Hello guys, in this lecture we will be starting with the electrical machines course. So the thing is, electrical machines are built upon the principle to transfer the electrical energy or to convert the energy from one form to another. Like, there are basically two kind of machines. One is the static machine like the transformer and other is the rotating machines like the motors and generators. The basic functionality of motors and generators is to convert the electrical energy into mechanical energy and vice versa. Whereas the transformer works on the principle of converting or transferring an electrical energy from one port to the other port. The common thing between all the electrical machines is this transformation of energy happens in the magnetic domain. Okay. So, first of all, the electrical or the mechanical energy is converted to the magnetic energy, then it is converted to the other form. So, the common link or the common domain between all electrical machines is the magnetic energy. That is why it becomes pretty necessary to understand the electromagnetic laws or the laws of electromagnetism so that we can understand the basic principle of operation of different type of machines. So what we'll be doing in this lecture is we'll be taking a look at some of the basic laws of electromagnetism that you might have studied in your 12th standard, so that when we'll be discussing the principle of machines, you will be more clear upon that. So basically, what does electromagnetism mean? Electromagnetism first of all means that electric field and magnetic field are interrelated. There are two type of fields, electric field and magnetic field. When these two mechanisms or these two fields are interrelated, it is termed as electromagnetism. That is, a time varying electric field can lead to induction of a magnetic flux density B or magnetic field H, and a time varying magnetic field can lead to an induced electric field. It is termed as electromagnetism. That is, electricity can be converted to magnetism and magnetism can be converted to electricity. Such sort of laws which relate between electrical domain and the magnetic domain are termed as laws of electromagnetism. So there are certain laws which are pretty necessary when it comes to machines. One such law is Faraday's law. Faraday says that whenever there is a time varying flux, then a EMF is induced in the conductor. So it talks about magnetic flux. So it says that whenever there is a time varying flux, that is, there is d phi by dt is not equal to 0. Whenever the flux varies with time, then a EMF is induced which is equal to d lambda by dt. Now first let us understand what is the difference between lambda and phi. Phi is called as flux and lambda is called as flux linkage. See, the thing is, suppose we take a coil, and if there is a flux produced phi, then this phi will be called as flux. And if there are n number of turns, then the thing is that phi is passing through each turn. So phi is linking to each and every turn. So total flux linkage would be equal to n into phi, since there are n number of turns to which phi is linked to each and every turn. So the total flux linkage lambda will be equal to n phi. This is the basic difference between flux and flux linkage. So Faraday states that EMF developed in a coil or a conductor upon application of a time varying flux is equal to derivative of the flux linkage. This term you must always remember, flux linkage and flux. Okay, this will come in handy when we will be studying power system also. So flux linkage is nothing but the total flux linked with n number of turns in a coil. Okay, so this is the law given by Faraday. Now the basic requirement for Faraday law to be satisfied. First we need a magnetic field. Okay, because we need a time varying flux, we need a magnetic field. This magnetic field will develop the flux. Next we need a set of conductors. Why we need a set of conductors? we need a set of conductors so that EMF can be induced across the conductor. This set of conductors can be in the form of a coil or in the form of simple conductor or a straight wire. So that's why we need a set of conductor. Next we need relative variation. That is, there must be some quantity that must be varying between the set of conductors and the magnetic field. Okay, there must be relative variation between these two things, then only a EMF can be induced as per the Faraday's law. Okay, there must be some sort of variation. Now let us see what kind of variations can be there. First is called as relative time variation. Relative time variation means that the magnetic flux density is a function of time. Okay, that means it is varying with time. So that is why we are calling it as relative time variation. So phi will be nothing but B of t into area. That means phi is also a function of time. So the EMF induced will be d phi t by dt. Okay. So this is called as statically induced EMF. Okay. Whenever we have a time varying flux, an EMF is induced in the coil, which is termed as statically induced EMF. Here the magnetic field varies with time. But the thing is, conductors must be stationary. Okay, means the conductors must not move. So the entire system becomes stationary. If conductors are stationary, that means the system is stationary. So this sort of EMF is induced in case of transformer. As I just now told you, transformer is a static type of machine. That is, it does not have any moving parts. It remains stationary with respect to time. So this relative time variation is observed in case of transformer, and the EMF induced will be called as statically induced EMF. Next, let us see what kind of other variation is. Other variation is relative space variation. That is, the position of the conductors must be changing with respect to magnetic field. Okay. Here, position of conductor changes with respect to magnetic flux density or magnetic field. Now, this sort of variation results in a dynamically induced EMF. Okay. So the EMF induced due to relative space variation between the magnetic field and the set of conductors is called as dynamically induced EMF, because the system here is dynamic. That is, it is changing its position. It is not stationary. So this sort of EMF will be introduced or will be induced when we will be talking about the rotating machines. Okay. So in generators and motors, we will be looking at the dynamically induced EMF. Okay. Because they have the rotating parts, so the set of conductors are being rotated with respect to a magnetic field, hence dynamically induced EMF will be present. Okay. So this is the two type of variations that are generally present in case of Faraday's law to induce an EMF. Now let us see both type of induced EMF one by one. For that, first we need to understand the concept of magnetic force. The thing is, whenever there is a charge Q which moves with a velocity v in a magnetic flux density B. So whenever there is a moving charge, okay, moving charge in magnetic field, then it experiences a force which is Q V cross B. Okay. The thing is, here this charge Q, it must be with respect to sign. Must be with sign. Okay. So electron will be written as minus E and positive charge will be written as plus Q. Okay. V is the velocity of the charge, B is the magnetic flux density in the region in which the charge is moving. So, whenever a charge is moving inside a magnetic field, it experiences a magnetic force given by Q V cross B. So, this sort of magnetic force acts on all the moving charges inside a magnetic field. Now, let us see how does this kind of force leads to induction of an EMF in a conductor. So, let us consider dynamically induced EMF. So, here what I am saying is, we have a conductor PQ or a coil or a loop which is moving with a velocity v inside a magnetic field. The magnetic field has been shown with a cross, that means it is inside the plane of board. The board that you are watching right now, it is inside the plane of that board. This is my B. Okay. So V is something like this and B is inside. Now, to find the force on the positive charge, what we will do? F is equal to QV cross B. Okay. So, positive charge will experience the force in what direction? To find the direction, what to do is, keep your fingers in the direction of V and curl them in the direction of B. If you curl them, then the direction of your thumb will be something like this. So, upwards, that means the magnetic force that will be acting will be upwards. Okay. Just keep your hand in the direction of V and curl your fingers in the direction of magnetic flux density. Then the direction of thumb will give you the direction of magnetic force. So, positive charge will feel a force upwards. Hence, they will start collecting on the top end of the conductor. Similarly, when we are talking about negative charge, it will experience a force like this, minus Q V cross B. Due to this minus sign, the direction of the force will be downwards. So, negative charge will start collecting here. Okay. So, we have a conductor with a positive charge at the top, negative charge at the bottom. That means an electric field will be induced. Whenever two positive or a negative charges are separated by a distance, an electric field is induced from the positive charge towards the negative charge. Because the electric field for a positive charge is away from the charge and it is towards a negative charge. So, electric field is induced. The thing is, the force due to electric field on a charge is, if it is positive in the direction of electric field, if it is negative in the opposite direction to the electric field. Now, since electric field is downward, force on a positive charge will be downward and force on a negative charge will be opposite to the field, that is upwards. But if you see, the magnetic field is trying to push the negative charge downwards, whereas electric field is trying to push the negative charge upwards. So, both the forces are opposite. So, till the time there is net force on the negative charge or the electrons will keep moving. But as soon as both the forces balance each other, then the net force on the charge will be 0. The charge will stop moving. So, we are considering the steady state condition when the charge is not in motion and the charges have stopped accumulating at both the ends. So, what I will say is, force on an electron due to electric field, that is E into E, should be equal to force on the electron due to magnetic field. As soon as this happens, the net force on the electron will be 0 and it will stop moving. So, induced electric field will be V cross B. Now, we know the potential difference in a conductor. If it has length L, the potential difference is nothing but E dot dl. So, it will be integral E dot dl. This will be my potential difference minus integral E dot dl. So, it will be V cross B dot dl with a minus sign. Okay. This leads to the expression BLV. Here one assumption I have made is V and B are perpendicular. If you see, V is rightward, B is inward, so they are perpendicular. So this is the voltage induced, that is called as dynamically induced EMF. It is also termed as motional EMF, that is EMF induced by virtue of motion of the conductor inside a magnetic field is termed as motional EMF. So this sort of EMF will be induced in the conductor when a conductor is being moved inside a magnetic field. Okay. So remember this expression, this sort of EMF is induced in all sort of the rotating electrical machines. Next, let us consider statically induced EMF. The thing is, statically induced EMF is nothing but EMF induced in the stationary conductor. So let us take a coil. If a coil is like this, a flux is passing through the coil. Okay. So what happens if flux is a function of time? Let us say flux is phi m cos omega t. Then the EMF developed is nothing but d phi by dt, that is minus omega phi m sin omega t. Okay. This will be the EMF induced in the coil, which is termed as statically induced EMF. But the thing is, the point to be remembered here is, while taking the derivative, we must consider flux linkage. So we must take number of turns here, that is n omega phi m sin omega t. So this sort of mistake you must avoid at all costs. Never take the derivative of flux directly, always consider the number of turns. Okay. So what I can say is, EMF induced is nothing but n into d phi by dt. Okay. This minus sign I will tell you from where it comes. This minus sign is in accordance with the Lenz's law. See, what does Lenz's law states? It states that induced EMF opposes the cause of induction. Okay. This is the basic definition of Lenz's law, that always the induced EMF will tend to oppose the cause of induction, so that induction does not happen. So that is why we are showing a minus sign here, that is induced EMF opposes the change of flux. The thing is, the EMF is being induced because the flux is being changing in the coil. So EMF will be induced in such a manner that it will try to stop the variation of flux, so that flux becomes constant and EMF is not induced in the loop. So that is why we show it with a negative sign. Lenz's law is one of the most important law when it comes to electrical machines, because all electrical machines will operate on single principle, that whatever the EMF is being induced, or whatever the current is being induced, or even whatever the torque is being induced, it will always oppose the cause of induction. That is why if we talk about generator, how does generator operates? We generally apply a prime mover. Prime mover is a machine which rotates the shaft of generator. It generates a prime mover torque TPM. Now, due to this torque, EMF will be induced in the generator. Okay. Since EMF is being induced in generator, there will be a current produced. Okay. This produced current or this induced current will oppose the cause of induction. Cause of induction is prime mover torque. So how does it oppose? It causes an additional torque, which is electromagnetic torque or induced torque. This induced torque will oppose the prime mover torque, that is they will be in opposite direction. So net torque will be prime mover torque minus electromagnetic torque. So that is why Lenz's law is so important, because whenever any induction happens in a rotating machine, it will happen in such a way that it opposes the cause of induction. Even in case of transformer, whenever a flux is induced in the secondary, it tends to reduce the primary flux, or it tends to cancel out the primary flux. That is how the Lenz's law is applied to all of the electrical machines that we will be studying in this course. Next, let us consider this self-induced EMF. what happens whenever the flux is varying through a coil and EMF is being induced in the same coil? That is termed as self-induced EMF. See, if I give you a coil and if we apply a time varying source here, then a flux will be induced. Flux will be varying with time, phi. Phi is nothing but a function of time. Then what happens? Suppose it has a number of turns n. Then flux linkage lambda will be equal to n phi. So EMF induced will be n into d phi by dt. Okay, this is my self-induced EMF. Okay, because the flux is varying through this coil, the flux is developed by this coil only, and the EMF is also being induced in the same coil. So this coil is itself responsible for the EMF induced in this coil. That is why it is called as self-induced EMF. It is itself responsible for this EMF. Okay, so we define a term called as self-inductance. Self-inductance is nothing but L is equal to phi by I. The thing is, if you want to derive the expression for self-inductance, first we need to find the magnetic flux density, which is mu naught Ni. N is number of turns per unit length. So it is mu naught Ni by L. This will be my magnetic flux density in the coil. Now, if you want to find the flux, flux will be nothing but B into A. Mu naught N A by L into I. If we want to find flux linkage, it will be N phi mu naught N square A by L into I. Now, self-inductance will be lambda by I, flux linkage by current, mu naught N square A by L. This will be the self-inductance of the coil. Next, let us consider mutually induced EMF. The thing is, when the flux produced by one coil links to the other coil and produces an EMF in the other coil, it is called as mutually induced EMF. See what happens. Suppose this is my one coil. Here I have applied a time varying source. It produces a flux phi which is linking in another coil, and EMF is being induced here. So this is called as mutually induced EMF. The responsibility of inducing an EMF in one coil is given to the other coil. One coil is responsible for the induction of EMF in the other coil. It is termed as mutually induced EMF. Let us consider number of turns N1, N2. So the thing is, mutually induced EMF will be N2 into d phi by dt minus N2 into d phi by dt as per the Lenz's law. So here we define a term called as mutual inductance. So what we call mutual inductance? M is equal to lambda 1 2 by I1. Okay, that is flux linkage in 2 due to 1 divided by current in 1. Okay, lambda 1 2 means flux linkage in coil 2 due to coil 1. I1 is the current in coil 1. So if we consider current in coil 1 as I1, B produced will be mu naught N1 I1 by L. Okay, so the flux produced will be mu naught N1 A I1 by L. What I am assuming is both the coils have the same cross section area and length. But now when we talk about lambda 1 2, it will be N2 into phi. So it will be mu naught N1 N2 A by L into I. So mutual inductance will be lambda 1 2, it will be I1 by I1, that is mu naught N1 N2 A by L. This is my mutually induced EMF in a coil which is linked to the flux produced by the other coil. So that is the two type of EMF induced. One is self-induced EMF, where the EMF is induced in the same coil which is carrying the current. Mutually induced EMF, where EMF is induced in the other coil which is not carrying the current. We define self as well as mutual inductance for these coils. Now, to decide the polarity of EMF being induced in the two coils, we use the dot convention. So what we do is, we look at the direction of flux in the both coils. Now here, current is entering here. To find the direction of flux, you have to curl your fingers in the direction of current. So if you curl your fingers here, it is going like this. So the flux will be like this. Okay. Curl your fingers in the direction of current, and the direction of thumb will denote the current. Like if you curl here, it will be like this. So the direction of thumb denotes the direction of magnetic flux. So phi 1 is in this direction. Similarly, in other coil also, the current is going in this direction. So flux will be in the same direction. So if phi 1 and phi 2 are produced in the same direction, then they will get added up. The net flux will be phi 1 plus phi 2. That is, they are supporting each other, or they are aiding each other. This is called as positive coupling. When the two flux add up or they help each other, it is called as positive coupling. So what we do is, we show the dots like this, here and here. That is, dots at both the terminals where the current is entering. It shows that if this terminal is positive, this will also be positive. Or what you can do is, these are the two coils, show dots here. If you show one here, show one here. Okay. Either at both the entering terminals or at both the leaving terminals. It is your choice. But the terminals must be same. Either current must be entering at both the terminals, or current must be leaving at both the terminals. It just shows the polarity of induced EMF. If this is positive, this will be positive. If this is negative, this will be negative. So that is how we show what polarity of the induced EMF will be there in the coil by using the dot convention. Next, let us consider this sort of coil arrangement. Here the current is going like this. So if we see in coil terms, it is something like this. So it will be here, phi 1. Okay. But if we talk about phi 2, current is going inside here, current is coming outside here. So it will have an opposite direction. It will be like this. So phi 1 and phi 2 are in opposite direction. The only way you can find out this direction is by right hand thumb rule. So just try to imagine, guys, how you will be curling your fingers around the coil to find the direction of the thumb. That will be the direction of the flux. Because it is not so easy for me to denote in this video lecture that how I can curl my fingers. So it is up to you to imagine. If we will be curling our fingers in the direction of the magnetic, in the direction of the current, then the direction of thumb will denote the flux. Now here net flux will be phi 1 minus phi 2, that is, both are being subtracted. It is called as negative coupling. So how we induce the dot? At one terminal we will show the dot at entering terminal, other at the leaving terminal. So if one dot is here, if two coils are like this, which are negatively coupled, if one dot is here, other will be here, or otherwise what you can do is, if one dot is here, other will be here. Okay, at the opposite terminal, one at the entering, other at the leaving. This will show if this is positive terminal, this is positive, this is negative, this is negative. Similarly here, if this is positive, this will be positive, this is negative, this will be negative. So that is how the EMF will be induced, or the polarity of EMF in both the coils. Next, the last thing that you need to understand in the magnetism for understanding the operation of machine is Lorentz force law. What does it say is, whenever a current carrying conductor is placed in a magnetic field, it experiences a force. The thing is, just now I told you, force on a moving charge is QV cross B. So whenever a conductor is carrying a current, if there is a conductor which is carrying a current I, that means electrons are moving like this and positive charge can be traveling like this. That means the charges are traveling inside the conductor. And we know if there is a magnetic field present and charges are moving inside that, then they will experience a force, due to which my conductor will also experience a force. So the force is I L cross B, where L vector is in the direction of current. Okay. The length vector will be in the direction of current. B is the magnetic flux density. So why we are using L vector is because current is a scalar quantity, so I cannot use the direction of current directly. That is why I am assigning the direction of current to the length vector. So that is what is my Lorentz force law. So let us summarize what we learnt in this lecture. First of all, what we saw is Faraday's law, in which we saw relative time variation and relative space variation. Then we saw dynamically induced EMF and statically induced EMF. Then we saw Lenz's law, which states that induced EMF opposes the cause of induction. Then we saw self-induced EMF and mutually induced EMF. Then we saw when EMF is being induced, to denote the polarity of EMF, we use the dot notation. And at last we saw Lorentz force law. So these are some of the laws that will be very helpful in understanding the operation of machines. So try to remember these and try to use the right hand thumb rule to find the direction of induced flux or induced torque. That will help you immensely when we will be understanding the operation of different machines. So this is all for this lecture. In next lecture also we will explore some basic concepts that are required for understanding the machines.